Example 12.3. How much current will an electric bulb draw from the 220 volt source if the resistance of a bulb filament is 1200 ohm? Okay, here we can see that a potential difference V is 220 volt while the resistance is of 1200, that is 1200 ohm. Okay, that is our resistance. Okay, it is denoted by R. How much current will an electric heated coil draw from the 220 volt? Okay, if there is the resistance of a heated coil is 100 ohm. Okay, here we have given that in a first. Okay, first it have given that V is of 220 volt. Okay, that is our potential difference. So our potential difference is 220 volt while resistance is 1200 ohm. Okay, so for that we have a equation. We have which equation? That V is equal to I R. Okay, in V is equal to I R we have value of V, okay, as well as we have a value of R. Okay, so from taking a subject of equation of I, okay, here we are doing a I as a subject of equation, so V upon R. Okay, we will get I is equal to V upon R. Okay, so here V is 220. Okay, so 220 upon 1200. Okay, so we will get I is equal to 0.18 ampere. Okay, here we are getting A is equal to 0.18 ampere. Okay, so our current will be 0.18 ampere. Same way, if we take a second one, how much current will an electric heated coil draw from a 220 volt sources if the resistance of a heater coil is 100 ohm? Okay, so for that we have taken I is equal to what? V upon R. Okay, same way. So here we will get 2.2 because our potential difference V is 220 volt. Same way, resistance is of 100 ohm. So our current will be 2.2 ampere. Now the second example, in that we have given that potential difference of a terminal of an electric heater is 60 volt when it is draw a current of 4 ampere. Okay, how much? Okay, 4 ampere. Our current is 4 ampere as well as our potential difference is 60 volt. What current will heater draw if the potential difference is increased by 120 volt? Okay, so first of all, in this we will find our resistance R. Okay, with the help of Ohm's law we are finding R because we have given a potential difference V is equal to 60 volt and electric current is 4 ampere. So on the basis of that we are finding our resistance R. It will be 15 ohm. Okay, now in the second case we can see that we have given a potential difference which is 120 volt. Okay, so here from R, okay, here in first case we are getting R is equal to 15 ampere and V is equal to 120 volt which is given. Okay, so on basis of that we can able to find out our I. Okay, so I is equal to what? Okay, V upon R. So we have a value of V, okay, which is 120 volt which is given. Same way R, okay, which we have find. Okay, so 120 upon 15, that will be 8 ampere. Okay, so from this we are getting a value of 8 ampere. Same way the third one is 12.5. Resistance of a metal wire of a length 1 meter is 26 ohm. So the metal wire of a length 1 meter is 26 ohm at 20 degrees Celsius. If the diameter of the wire is 0.3 mm, what will be the resistivity of a metal at that temperature. Okay, predict the material of a wire. Okay, we are given a resistance. Okay, we have given a resistance of 26 ohm. Okay, from the question we are getting that resistance is our 26 ohm. Okay, from the data we are getting that R is equal to 26 ohm. Our diameter D is of 0.3 mm. If we convert it in a meter, okay, so it will be 3 into 10 raised to minus 4 meter. Okay, same way our length is 1 meter. Okay, which is already given. Okay, now we have a formula. Okay, we have a formula of a rho. Okay, which I have already studied in a previous lecture, that rho is equal to RA upon L. RA. So A is denoting area. So area will be pi d square. Okay. What will be the pi r square? Okay. Our area will be A is equal to pi r square. Okay. But if we take directly in a d, okay, diameter. Okay. So it will be pi d square upon 4. Okay, so here you can see that 4 is divided. Okay, so r, okay, which is as it is a, which is pi d square. Okay, we are converting r into d, so d square upon 4n. Okay, so it will be r pi d square upon 4n. Okay, so from this substituting the value of given value r, which is 26, okay, pi, okay, it may be 22 by 7 or 3.14, okay, whatever, okay, it will be right. D, okay, which we have given 1, 4, D, sorry, D is given 3 into 10 raised to minus 14. Same way L, which is given 1. Okay, on substituting all the value we will get our answer, which is 1.84 into 10 raised to minus 6, 10 raised to minus 6 ohm meter. Okay, so resistivity of a metal will be 1.84 into 10 raised to minus 6 ohm. Now the example 12.6. A wire of a given material having a length L and area of a cross section A has a resistance of 4 ohm. Okay, our resistance is 4 ohm. What will be the resistance of another wire of the same material having a length L by 2 and cross section area is 2A? Okay, so in first case we have given that resistance R1 is equal to 4 ohm, okay, which we have given 4 ohm. Okay, and we have a formula rho L upon A. Okay, so we have a formula rho L upon A. Same way, our second resistance is R2, okay, in which we have given value of L is equal to L upon 2. Okay, here given L upon 2. Okay, so we are substituting in place of L, we have substituted L upon 2. Okay, same way our area of cross section, okay, which is given 2A, double. Okay, so double, in place of A we have written 2A. Okay, now if we substitute and simplify the given equation, then we will get 1 upon 4 R1. Why R1? Because here rho LA will be R1. So it will be R2 is equal to 1 upon 4 R1. Okay, so it will be 1 upon 4 R1. Okay, so our value of R1 is 4 ohm. So substituting that, we will get R2 is equal to 1 ohm. Okay, now the resistance of a system of a resistors. Okay, in preceding a section we run about some simple electric circuit. We have noticed how the current through a conductor depends upon its resistance. and the potential difference across its end. Okay, how all of them are depending on each other. Okay, we have studied that. In various electrical gadgets, we often use resistor in various combinations. Okay, in various type of gadgets, we are using it in a various form. We now therefore instinct to see how Ohm's law can be applied to the combination of a resistors. Okay, here we are using a resistors, okay, that can be connected with the series or parallel. Okay, we will study that only. Okay, two methods of joining resistors are there. Okay, how many? Two methods are there. So the electric circuit in which three resistors having resistance R1, R2 and R3. Okay, we are using three resistance. How many resistance? Okay, three resistance which are R1, R2 and R3 respectively are joined end to end. Here the resistors are said to be connected in the series. Okay, in figure 12.6, okay, which we will see now. Okay, here you can see that, okay, resistors are connected R1, R2 and R3. Okay, that are connected in the series. Okay, that are in a series. You can see that this is a series connection. Okay, so in this we can see that there is a present of a ammeter, okay, voltmeter, present of a ammeter, voltmeter, key, battery, okay, and the direction of a flow of a current is from this way. Okay, positive to negative. Okay, as you can see, figure show a combination of a resistor in which three resistors are connected together between point X and Y. Okay, here you can see that three of them are connected between point X and Y. Okay, here it is X and here it is Y. It is connected in between them. Here the resistors are said to be connected in the parallel. Okay, now the second one. Okay, here you can see in second one here. Okay, in this you can see, in this you can see that, in this you can see that R1, R2 and R3. Okay, three of them are connected with a parallel connection. Okay, here we will see it as a parallel connection. Okay, so you can see that from X and Y, okay, between X and Y, okay, three are there, 1 2 and 3, 1 2 and 3. Okay, so this connection is known as parallel connection. Okay, if it was in series R1, R2 and R3, okay, these are said to be a series while this is known as a parallel. Okay, and this is a series. Okay, in series you can see that R1, R2 and R3 are in a straight line or in a series connection, while in a parallel you can see that three of them are in a parallel form. Okay, and same, okay, circuit will be as it is. Okay, it will be ammeter, okay, key, battery, okay, and voltmeter. Okay, all of them are present in it. So this was the two series connection as well as parallel connection. Okay, connection of a different resistance with each other. Okay, so there is a possibility of two connection, parallel connection and series connection. Okay, now resistors in series. Okay, what happened to the value of a current when a number of resistors are connected in the series in a circuit? Okay, if the number of them are connected in the series in a circuit, what will be their equivalent resistance? Let us try to understand this with the help of following activity. Okay, here you can see, okay, that three of them are, okay, three of them are connected in a series. Okay, Three of them are connected in a series connection. Okay. You will observe that the value of current in the ammeter is the same, independent of its position in the electric circuit. It means that in a series combination of resistors, the current is the same in every part of circuit, or the same current through each resistors. Okay, so here you can see that in a series connection there will be a same I. Okay, I will be constant for all of them. Okay, equal current will flow in all the resistance. So you will observe that potential difference V is equal to the sum of potential difference V1, V2 and V3. Okay, if we want to find a total potential difference, okay, it will be V1 plus V2 plus V3. Okay, so total potential difference will be a sum of a three potential difference of a different resistance across individual resistors. Okay, so individual resistors containing potential difference. Okay, three of them will be sum. Okay, and we will get a total potential difference by the sum of a three different potential difference. In the electric circuit shown in the figure 12.8, let us I be the current through the circuit. The current through the each resistor is I. Okay, so current is passing from the each resistors is I. It is possible to replace the three resistors joined in the series by a equivalent single resistor of a R. Okay, such that potential difference V across it and the current I through the circuit remain the same. Applying the Ohm's law entire circuit, we will get V is equal to IR. Okay, here V is equal to IR. In V is equal to IR, you can see that V, which indicate a total potential difference in a circuit, I indicate what? Okay, current flowing in the circuit. Why? Because in a resistor, if the resistors are connected in the series, at that time you can see that current is flowing in each of the resistors will be equal. So I will be constant for all the, or equal for all the resistors or resistance, and same way total resistance will be R. Okay, so our Ohm's law for total potential difference is equal to V is equal to I R. Okay. Now, if we individually apply a Ohm's law, okay, then what will be the value? That will be okay. Here you can see that V1 is equal to I R1. Okay, that is for first resistors. Okay, so V1 is equal to I R1. Okay, same way for the second resistors, potential difference will be V2 and resistor will be R2. Okay, so here you can see that I is equal in all the three resistors, potential difference as well as, okay, the same way V3 is equal to I R3. Okay, now if we apply Ohm's law, okay, now applying Ohm's law, okay, we know it that V is equal to V1 plus V2 plus V3. Okay, so here our value of V1 is IR1. Okay, same way V2 is IR2 and V3 is IR3. Okay, substituting that we will get this equation. Okay, same way our total resistance will be R is equal to R1 plus R2 plus R3. Okay, so in this you can see that we can conclude that when several resistors are joined in the series, the resistance of a combination R is equal to the sum of their individual resistance. Okay, which we are getting. Okay, so if we want a sum of a resistance, it is denoted by RS. Okay, then it will be the addition of individual resistance which are there. Okay, R1 plus R2 plus R3. Okay, Same way example 12.7. In example 12.7 you can see that an electric lamp whose resistance is 20 ohm. Okay, here electric lamp contain a resistance of 20 ohm. Okay, and a conductor of 4 ohm. Okay, now in a conductor which you are getting as 4 ohm are connected to a 6 volt battery. Okay, the battery is of 6 volt. Okay, calculate the total resistance of a circuit and the current through the circuit and potential difference across the electric lamp and conductor. Okay, so the resistance of an electric lamp is R1 is equal to 20 ohm. It is 20 ohm. Okay, how much the resistance of electric lamp is 20 ohm. Same way the conductor is R2 is equal to 4 ohm. Okay, so total resistance will be R is equal to R1 plus R2. Why R1 plus R2? Because it is connected in the series. So it is 20 ohm plus 4 ohm. So it will be 24 ohm. So total will be 24 ohm. Okay, the total potential difference across the two internal of a battery, it will be V is equal to 6 volt. What? Okay, V is equal to 6 volt. So it will be 6 volt, which is given. So by applying Ohm's law, I is equal to V upon Rs. So it will be current is flowing 0.25 ampere in whole circuit. Now applying Ohm's law in the electric lamp and conductor separately. Okay, if we apply separately, okay, so V1 is equal to how much? Okay, V1 is equal to 20 ohm plus 25 0.25 ampere. So the volt will be V1 is equal to 5 volt, and same way for the second one V ohm. Okay, V ohm is equal to 0 multiplied by 0.25, it will be 1 volt. Okay, because we have a formula V is equal to I R. Okay, for I will be 0.25, which is constant for both of them, and R, okay, which is the resistance of a conductor, which is 4 ohm. In same way for V1 it will be 20 ohm. So separately we have find potential difference, okay, of a lamp and conductor both. Okay, suppose that we like to replace it by the series combination of electric lamp and, okay, then it will be, if we want to find total, R is equal to V upon I, then it will be 6 volt divided by 0.25 total volt, which is 6 volt. Why? Because 5 volt plus 1 volt, it will be 6 volt upon 0.25 ampere. So total resistance will be 24 ohm. Okay, now the resistor in parallel. Okay, in parallel connection we will see a resistor. Now let us consider the arrangement of a 3 resistors joined in the parallel combination. Okay, here you can see that 3 of them are connected in parallel connection. Okay, R1, R2 and R3, and 2 junctions are there, A and B, 2 AND are there. Okay, so for that R1, R2 and R3, 3 of them are connected in the parallel. Okay, and voltmeter, okay, which are connected same way, battery is connected and ammeter is connected to measure a current which are passing from the circuit. How much current is passing from the circuit? It is observed that the total current I is equal to the sum of the separate current through the each branch of combination. In series we have seen that I is constant for all of them, equal for all of them, but in the parallel we will see that the current will flow different in different resistance. Okay, each of them will carry a different amount of current. Okay, or carry out different amount of current from a different resistance. Okay, so it will be I is equal to I1 plus I2 and I3. Okay, I1 current, okay, I1 current is passing from the resistance R1, I2 current is passing resistance from the R2, and I3, okay, is connected or passing from the resistance R3. Let Rp be the equivalent resistance. Okay, we have taken Rp, which is our total resistance. Okay, so it will be R1 plus R2 plus R3. No, because we have to find out this is for series connection. Okay, this is for series connection. For the series connection, we have total resistance is equal to R1 plus R2 plus R3. But what about the parallel connection? For that we have to find this. Okay, for that we have to find this. Okay, this is for RS. Okay, which we say it as RS. Okay, for RP we have to find that. Okay, we have formula I is equal to V upon RP. So here you can see that in a Ohm's law, okay, I1 is equal to V upon R1. Same way I2 is equal to V upon R2. Same way I3 is equal to V upon R3. So if we take a value, okay, V upon RP, which is our V upon R1, because here in this potential difference will be different. In series we have seen that potential difference. Okay, here you can see that potential difference in three of them are equal, but in series connection we have seen that potential difference is different for different resistance. So here if we take V, which is common, okay, because which is equal in all of them. Okay, so we have taken V as a common, so we will get 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Okay, so thus we may conclude that reciprocal of equivalent resistance, okay, reciprocal of equivalent resistance of a group of a resistance joined in a parallel is equal to the sum of the reciprocal of individual resistance. Okay, individual resistance reciprocal, okay, sum of the individual resistance reciprocal will be equal to sum of the resistance, total resistance. Okay, so we will get this. Now example 12.8, in this we can find that 5 ohm, 10 ohm and 30 ohm resistance are connected. Okay, and we have a volt 12 volt, potential difference is 12 volt. Okay, we have to find each resistors, okay, how much current is passing. So here we have given R1 is equal to 5 ohm, R2 is equal to 10 ohm and R3 is equal to 30 ohm. The potential difference is 12 volt. Okay, so from this we can find that I1, okay, is equal to I is equal to V upon R. Okay, so it will be 2.4 ampere. Same way, individually if we find a current, then I2 is equal to 12 volt upon 10 ohm, because our second one is 10 volt. Okay, so it will be 10 volt. Same way for that it will be 1.2 ampere. Same way for the third one it will be 0.4 ampere. Okay, so the total current in the circuit will be I is equal to I1 plus R2 plus I3. Okay, so if we add we will get 4 ampere. That is our total current passing from the circuit. The total resistance Rp is given below. So this will be our total resistance, okay, because it is in a reciprocal, okay, which we have already find. So it will be 3 ohm. Why 3 ohm? 1 upon Rp is equal to 1 upon 3. Okay, if we take, then Rp is equal to 3.
Three resistors of different values connected in series. How do we know they are in series? Because they connected one after the other, forming just one path and not multiple paths. Let's perform a small activity now. Close the plug key and note the ammeter reading with these three resistors connected in series. Let it be I amperes. Next, place the ammeter somewhere between resistors R1 and R2 and note its reading. Similarly, place it between R2 and R3 and note the reading. What you will notice is that the current will be I amperes in each case. Yes, the current is constant at every point in the circuit. It tells us that in a series combination of resistors, the current flowing is the same throughout. Okay, now let's remove the ammeters which are between the resistors and try out something else. Now insert a voltmeter across the start of the first resistor and the end of the third resistor. Now plug the key and note the potential difference across the resistors. Let's say it's V volts. Now take out the plug key and disconnect the voltmeter. Now we insert 3 voltmeters in the circuit like this, one across each of the resistors. Now we plug the key and measure the potential difference across each of the resistors. You will notice that the potential difference across each of the resistors is different. Let's call them V1, V2 and V3 respectively. Even though the voltages are different, you will notice that the potential difference V will be equal to the sum of the potential differences V1, V2 and V3. This helps us derive something very important. Look at the entire circuit first. The potential difference is V volts and the current flowing through it is I amperes. Let's say these three resistors together form a resistance R ohms. We still don't know what R is, but we've just assumed all three together to provide a resistance of R ohms in this circuit. So according to Ohm's law, we can say that the V is equal to I times R. This was the entire circuit. Can you try applying the Ohm's law to each resistor separately? It's easy. For the first resistor, the potential difference is V1 volts. The current flowing through it is I amperes and the value of the resistance is R1 ohms. Applying the Ohm's law for the first resistor, we get V1 equal to I times R1. Similarly, for the other two resistors, we apply the Ohm's law to get two more equations. Now we can substitute the values of V, V1, V2, V3 in the first equation to get the result we need. V is I times R, V1 is I times R1, V2 is I times R2, and V3 is I times R3. Dividing both sides by I, we get the value of R as this. What did we just get? When two or more resistors are connected in series, the overall combined resistance R is the sum of the individual resistances. Now you understand why the resistance increases